Hi, everyone. Just addressing your feedback today about the Chatelier's principle and equilibrium shifts. What exactly is shifting backwards and forwards? What is the solution doing? So we defined an equilibrium state as a point when concentrations aren't changing anymore. There's still a forward reaction and a backwards reaction, but those reaction rates are occurring at the same rate. And when that occurs, law of mass action tells us that the concentrations the ratio of their concentrations is equal to some constant. And their concentrations are constant, and they will be with time if the system is at equilibrium. Until you disturb the equilibrium in some way. Disturb by stressing it, either by, well, we talked today about changing concentration. So if I suddenly increase the concentration of the products, the question is, okay, I have disturbed the system from equilibrium. How does it respond to that disturbance to reattain equilibrium? That's what we mean when we're talking about a shift. So case in point, if I had some very, very basic reaction, A equilibrium with B, then its law of mass action would be concentration of B over A. And if I disturbed it by, say, increasing the concentration of B, meaning that I made my numerator larger than it was before, well, then the proportionality here will no longer be equal to the equilibrium constant. The only way that it can equalize is if the concentration of A also increases, and they have to, in this case, increase proportionally to each other. So what we'll say is, okay, if you disturb the system by increasing the concentration of B, the reaction shifts, quote unquote, to the left, is what we say, that you start generating a higher or a larger amount of reactant molecule. So when we say shift, we're basically just saying, okay, if I change the system, change the reaction system in one part by either adding a product, removing a reactant, how do the concentrations of everything else change in response to it? If the concentrations of the reactants increase in response to the change, we say that the reaction shifts to the left, that the equilibrium shifts to the left. In terms of what is the solution doing, the solution's concentrations are changing in response to you enforcing some change. In what case does the rate forward equal to rate backward change to something like this, where, say, rate forward is suddenly less than so anything that could somehow either increase the rate of the backwards reaction or decrease the rate of the forward reaction would result in that particular scenario. So it could be something, well, we imagine that the backwards reaction should depend on the concentration, the rate of the backwards reaction should depend upon the concentrations of the products, so I could increase their concentration, or I could try decreasing the rate of the forward reaction by removing reactants. If I remove the reactants, okay, I decrease the concentration of A, then the system will naturally shift this way to reproduce it. All of a sudden, I've made my denominator smaller, so I need to make my numerator smaller. So I will lose B, the reaction will shift and generate a little bit more A to make up for the A that I lost. So there's a couple of ways that you can imbalance these rates of reactions. Either the simplest way is, well, we remember that a rate depends, should be proportional, well, it should be, I'll just say this, it should be equal to a rate constant, and it should be proportional to concentrations. So anything you can do that can change the concentration. So if you're dealing with solutions, that's normally you add some solute. You can also dilute it by just increasing the volume. So you add solvent, and that will change the concentrations. If you're dealing with a gas, you can increase the pressure in some way, or you can expand the system. Again, you're lowering the pressure when you expand the volume of it. So all of those will in some way change the concentration. The rate of a reaction is also dependent on the equilibrium constant, which, according to Arrhenius' theory, is dependent on temperature. So I didn't get a chance to talk about temperature explicitly today. I'm going to make a separate video, and I'm going to post that, and I'm going to ask people to watch that over the weekend. But point being that you can imbalance the equilibrium by changing temperature. And that's going to cause the rates to change in a slightly different ways. One of the rates is going to speed up more than the other one as you change the temperature, and that will cause the reaction to shift again. How do you determine what goes up and down based on what is added or removed? So generally speaking here, I'll use this. I'll make this just a little bit more. Actually, you know what? I'll use this. I'll use an example I spoke about today. So how do you determine how the system responds when you add things or remove things? So let's start with adding. We'll just talk about what happens when you add, you increase concentration. I actually want to emphasize that because when I say add reactants, add products, the key point there is we assume reaction rates are dependent on concentrations, not just dependent on amounts. The concentration obviously depends on amount, but it also depends on the volume. So just adding reactants or just adding products may or may not change or shift the concentration, or shift the reaction, shift the equilibrium. Changing concentration does. So let's work with that. Let's say I somehow increase the concentration of a product. If I increase the concentration of a product, that's going to shift the reaction in the opposite way. Basically, Le Chatelier's principle says if you stress a system, the system will respond to minimize that stress. So it goes in the opposite way of that stress in some way. So if I increase products, natural tendency for the system is to increase, in response, increase the concentration or increase the amount of reactants. So in this particular case, yeah, I'll work with this one. Yeah, this particular case, if I increase the sodium concentration, the reaction tends to shift to the left. Or if I somehow lower the concentration of a reactant, all of a sudden of a product. I've lost product, so I'm removing product. Now I have fewer products available than would be required for me to have, for my my quotient here to be equal to the equilibrium constant. The only way I can fix that is either by, so if I lost products, the only way I can fix that is by losing reactants. So I will drop the amount of sodium chloride. By dropping the amount, I mean that it dissociates. It goes from being an NaCl solid form to being in the form of sodium plus and chloride minus. Again, the Chatelier's principle basically tells you that if you stress a system in one way, it will change to negate or minimize that stress. Still don't understand. Okay, let's deal with this because there were a couple of questions about this. I still don't understand why adding HCl. Why does adding HCl shift this reaction towards the reactants? And that's a reasonable question because it doesn't look like HCl is any one of the species in this equilibrium system. except that we understand HCl is a strong acid, and in solution, HCl splits into hydronium ions, hydrogen ions, and chloride ions. So when you have a solution of hydrochloric acid, it's not actually in the form of HCl. Most of it is in the form of chloride ions and hydronium ions. So when you add a solution of HCl, you are essentially adding chloride ions and hydronium ions to a solution. So in practice, what you're doing when you add HCl is you're adding chloride ions, so you increase the concentration of the chloride. All of a sudden, I have an excess amount of products. That means I have too many products, so I need to increase the amount of reactants, very, very generally speaking. Or rather, I should say increase the concentration of reactants. Why is it that if the reverse rate is faster, the reaction shifts towards products? So actually, let me say that again. Why is it if the reverse rate is faster, the reaction shifts towards products? It shouldn't actually shift towards the product. If the reverse rate is faster, then that means you're producing more reactants, and the equilibrium system is shifted towards the reactants. So I may have misspoken during lecture, and if that's the case, I apologize. And if you're confused, if the person who asked this was confused by that statement, you were right to be confused because increasing the rate of the reverse reaction actually should result in the reaction being shifted towards the reactants, not the products. Why is the equilibrium constant for HCl larger than the equilibrium constant for HF? Why don't the coefficients matter? Okay, so that's a good fundamental question, and let me complete that by writing the other equation here, which is HF aqueous dissociating into H plus and Cl minus aqueous. So I think a common misconception occurs here, which is that you start with the equilibrium, you start with the law of mass action, and then you have this equilibrium constant. And people are people become, acclimated to calculating things, calculating equilibrium constants. And it looks like, okay, you plug in the concentration of the products, you plug in the concentration of the reactants, and you get the equilibrium constant. And if you were doing that, then yeah, you would say, okay, I might know the concentration of H plus and Cl minus, I might know the concentrations of H plus and fluoride minus. And you would need to know their molar coefficients so that you could calculate K. But that's not quite how it works, conceptually speaking. I would say that it's wrong to look at it from that perspective. We don't think that the concentrations determine the equilibrium constant. It's the other way around. The equilibrium constant determines the concentrations. The equilibrium constant is characteristic of a particular reaction. These guys naturally have different equilibrium constants. It depends upon things like the energetics. The short answer is it has to do with the energy change of breaking a hydrogen chloride bond versus breaking a hydrogen fluoride bond. This bond is a little bit stronger than an HCl bond, so the reaction tends to not go as much to the products for HF as it does for HCl. And so naturally, following from that idea, we assert that the equilibrium constant should be smaller for HF. The equilibrium constant tells you characteristically whether a reaction is skewed towards the reactants or skewed towards the products, whether it tends to do that naturally or not. HCl is a strong acid. We had previously taught to you the idea of strong acids versus weak acids. And when we described them to you initially, we said we use words like, okay, HCl completely dissociates. HF only partly dissociates. Something completely going, as opposed to only partly going, is kind of related to the value of the equilibrium constant. The equilibrium constant tells you, okay, proportionally, are you mostly in the form of products or mostly in the form of reactants? HCl is a strong acid, it completely dissociates, so it's mostly in the form of the products of this reaction. So I can assert then that the equilibrium constant for HCl is very, very large because we know it's a strong acid. That's how I was able to make that determination. And furthermore, because HF is a weak acid, it doesn't strongly favor the products. It doesn't completely dissociate. A lot of HMol, if you have a solution of hydrofluoric acid, you will have a significant amount of HF molecules dissolved in solution, and you will have some fluoride ions and hydronium ions. You'll have all three of these species in solution. So there's an appreciable concentration of HF, and there's a reasonable concentration of H plus and F minus. So you have something that is not entirely skewed towards the products. So it's a relatively small, you have a relatively large denominator, so it's not a terribly large equilibrium constant. Again, that's building up, that assertion is building upon some intuition by knowing that HF is a weak acid. Do the coefficients matter? The coefficients matter in terms of how do you calculate what these reaction concentrations are, and you'll get some more experience with that later. The coefficients matter in terms of predicting exactly what the concentrations will be. They don't matter in terms of predicting what the equilibrium constant is. That is determined by chemical energetics, which we'll talk about in the next few weeks. Why can't sodium chloride saturated solution increase the amount of sodium plus and chloride plus? Why can't you, by adding more sodium chloride, can't it become supersaturated and be driven towards the product? Yeah, so that's a good question, because we've talked about, oh, you can make a supersaturated solution. And that's true, except a supersaturated solution is not at equilibrium. A supersaturated solution eventually crashes out. So if you've ever seen things like, I'm thinking of something really crazy, Great Salt Lakes or the Dead Sea, those solutions have the Dead Sea has very, very high sodium chloride content, high salt content. And so it tends to crash out as water evaporates. It becomes supersaturated, so it naturally crashes out. Point being that, maybe not a great example. Point being that, yeah, you can create a supersaturated solution, but the supersaturated solution is not an equilibrium system. It eventually will crash out of solution. And we saw that when I showed you, oh, you have a supersaturated solution. If I disturb it in some way, the solute crashes out until I have a saturated solution again. The characteristics of that saturated solution are determined by the equilibrium constant. So you can't change the value of the equilibrium constant. So you can't change the concentrations of sodium and chloride, is what I'll say there. Why does adding solid sodium chloride have no shift in the equilibrium? Could you explain that again? Yeah. So the real tricky part here, and I admit this is tricky, is that when we talk about amounts of products, amounts of reactants, rates and whatnot, we talk about them being determined by concentrations. And it's very easy to equate concentration and amount of something. But those are not, they are not the same. So let me explain what I'm talking about here. And again, I erased this earlier, but I'll put it up again. Concentration of A is moles of A over the volume of my solution. So concentration and amount are proportional. As one increases, so does the other. but concentration also depends on volume. So in this sodium chloride system, I had solid sodium chloride, and I had sodium plus and chloride minus hanging out in the solution. This was the solution, this was a solid here. In theory, the equilibrium constant for this reaction, or rather, I shouldn't say the equilibrium constant, the law of mass action for this reaction has the following form in theory. I'm putting a little S there to emphasize this is for the solid sodium chloride. One way to think about this is that this is a heterogeneous equilibrium. It's actually not a single system, but an aqueous system equilibrium with a solid system. Short answer here I'm going to get to is that the concentration, even if you add more sodium chloride, you add more solid, you don't change the concentration of solid sodium chloride. Solid sodium chloride is solid. Its density, the mass of it per unit volume, is a constant. Just because I add more sodium, I add more table salt, doesn't mean that I'm changing its density. I increase the moles of it, but I'm also correspondingly increasing the volume, because as I add more, the lump gets larger and larger. So the amount of it goes up, but so does its volume. And so as a result, its concentration is fixed. It's a constant. So to some extent, it doesn't have any sway over the concentrations of sodium chloride and sodium plus and chloride minus. That's kind of the short answer. Is basically that you can add NaCl, but you're not changing the concentration of NaCl. And so in that respect, you aren't actually disrupting the equilibrium system, or the equilibrium condition. The equilibrium condition describes concentrations which are variable in some way. Yeah, that's what I'll say. Okay, better example, or here's another example, or here's something that will, if you don't believe me about this, here's a different way to think about this. Consider this equilibrium process. So I have liquid water in equilibrium with gaseous water. If I were going to write a law of mass action for this, I would predict that it would be K is equal to the partial pressure, well, it's products over reactants. Products in this case are going to be the gas. So it's just the partial pressure of the water, and then the liquid doesn't factor into the equilibrium expression because it's a liquid. Its concentration is constant. It doesn't have a concentration and it doesn't have a pressure. So let me actually describe what this system looks like. So I have liquid water, and then I have gaseous water, and this implies then that whatever the equilibrium partial pressure there is, that is the vapor pressure of water. The vapor pressure is the pressure that builds up when you have a liquid in equilibrium with its vapor, and that's what I'm describing with this process. And here's a question: if I have a sample of water and I increase the amount of water, how does the vapor pressure change? I worked through a problem or in class where I kind of showed this to people, and I recognize that it seems counterintuitive, but I'll assert to you that, remind you that the pressure here was constant. That vapor pressure is determined naturally by whatever liquid water's vapor pressure is. It doesn't matter how much water there is. It's only determined by this natural equilibrium constant, which happened to be water's vapor pressure. So that's another example where, okay, you can have one substance which has a finite concentration, which is somehow separated from the parts of your system that can vary in concentration. So here's one part, here's another part. We can think of this as a heterogeneous, meaning it's not all a single phase. And that's one example of where why changing the concentration, or rather changing the amount of one of the reactants, doesn't affect the equilibrium in any way. After stressing, the system doesn't naturally shift to equilibrium. Yes, and that is in essence what Le Chatelier's principle is. If you stress the system in some way, it will naturally shift backwards in opposition to that stress. Can an equilibrium run out of one of its reactants? Can you run out of sodium? If I keep adding something like, and you guys are going to do this next week in lab, if I add silver ions to completely remove the chloride, can I run out of sodium? In theory, no, not 100%. That reaction also doesn't go to completion, so you never completely remove the chloride ion, so you can't completely remove any of the sodium ions or anything like that. But in theory, yes, you can essentially run out of one reactant. I can keep adding silver until I completely remove the chloride, and vice versa. Or I could keep adding HCl. Well, the HCl, that's the same thing as chloride. I can keep adding that. That will increase this, which will shift the reaction that way, and then I'll lose sodium. I could keep doing that until I essentially, keyword there is essentially, run out of sodium. In theory, you can never completely run out. But in practice, it can be it could be a negligibly small amount. What are the characteristics of a reaction shift? Is it determined by solubility rules, or whether something is a weak or strong acid? The characteristics of a reaction shift are any changes in concentration. That's what we consider to be a reaction equilibrium shift, is that I add something, I add a reactant, or I add a product, and the concentrations of everything else changes in some way. That's what we consider an equilibrium shift. Is that determined by solubility rules, or whether something is a weak or strong acid? No. Whether something is a weak or a strong acid, or whether something is soluble or insoluble, is determined by the value of the equilibrium constant. How a reaction shifts is determined by the form of the law of mass action. So there's a couple of things to think about here. If you want to think about this more mathematically, this is literally a number. It has a value. That value doesn't change. It's a constant, hence the term equilibrium constant. That number, that constant, is part of an equation. Just like when I was dealing with Henry's law, I'm looking at things that we've dealt with that were similar to this. When we dealt with Henry's law told us that the concentration of a solution in a gas was equal to some Henry's law constant times the pressure of that gas above that solution. So the concentrations could change and the pressure could change, but the Henry's law constant was constant, and that constant was characteristic of the nature of the interactions between the gas and the liquid, how soluble they happened to be with each other. And again, that constant is just a number. It doesn't change in any way. But the equilibrium can shift in the sense that if I increase the pressure of, so when we were looking at making soda water, if I increase the pressure of the CO2 above the water, the concentration of the CO2 in the water also increased. So concentrations and pressures change. Whether something tends to be soluble or not, that's determined by the equilibrium constant, or the Henry's law constant. The Henry's law constant is an equilibrium constant. What is the point of these equations? That's a good question. Partly if you are comfortable interpreting an equation, if you're comfortable with thinking, well, uh, looking at it and saying whether things are proportional or inversely proportional, that gives you a sense of thinking how the system will change in some way. We will eventually start using the equations to do some actual calculations. We will be doing some calculations later. You can use them to, you can manipulate them and talk about, okay, how does the relative ratio of two species change as I change the concentration of a third species? So that's actually something that you'll look at when you deal with indicators. Indicators are, well, I don't want to talk too much about indicators right now. But the point being that you can use these equations to describe how is one property related or correlated with another property. Okay, I can look at this to say that the concentrations of sodium and chlorine in a solution are independent of the amount of solid salt around it. So case in point here, that's something I can get out of this equilibrium expression. The equilibrium expression tells me that at equilibrium, sodium and chloride have a preferential product, which is their equilibrium constant. That is independent of the amount of solid sodium chloride. So I can make that pile bigger and bigger. It's not going to change the equilibrium concentrations. So in that sense, they are useful. At least I think they're useful in the sense that you can look at an equilibrium. You can look at a balanced chemical equation. You can construct the law of mass action for it, and then you can predict how that equilibrium system will respond to changes. You can also use it to calculate equilibrium concentrations, and you will do that as well soon. Does the equilibrium constant depend on the forces needed to break apart reactants? Is it related to intermolecular forces? Yes, it is. I think I mentioned that already, but I'll mention it again. The actual value of the equilibrium constant, that characteristic value, is dependent upon the strengths of molecular bonds, the strengths of intermolecular forces. So case in point, water has very, very strong intermolecular forces with itself. And when it's in the liquid form, everything is tightly packed together. I can make a little picture about that simply because I know it's a liquid, and in liquid everything's packed together. For water vapor, everything is separated. So I need to overcome intermolecular forces when I do this when I'm looking at this particular equilibrium expression. Then the value of the equilibrium constant depends on how strong these intermolecular forces are, how tightly bound they are to each other. Stronger the intermolecular forces, stronger the bonds. Well, not necessarily the higher the equilibrium constant. In this particular case, the stronger the bonds, the lower the equilibrium constant. The equilibrium constant is, well, what's the pressure of water at equilibrium? If these bonds are really, really tight, they don't really want to separate each other to go into the vapor phase. So the point is that, yeah, they are related. Do we need to refamiliarize ourselves with solubility rules? Need is a strong word in the sense that I'm going to try to not directly test people on it, but you will end up using them in your labs next week and in your cation analysis lab later on in the semester. So I would say refamiliarize yourself with the solubility rules. You're going to end up using them again anyway. I don't plan on giving questions. I don't plan on giving questions that require you to know the solubility rules. If I do give those questions to you, I'll give you a table of solubility rules. I don't want people to have to memorize solubility rules. I'm not big on memorizing a bunch of rules like that. But I like people using rules. So I would say short answer, kind of. You should consider refamiliarizing yourself with solubility rules, but I'm not going to mandate that people do it. You will probably end up refamiliarizing yourself with them simply because of your lab work that you'll be doing. Okay, that's that for this feedback video. I'm going to have a separate video in just a little bit talking about how temperature affects equilibrium. And yeah, I will see everybody on Monday otherwise. Have a good weekend.